So finally, we are on to the discussion of a very important concept in solid state physics or statistical mechanics in general, what is known as the density of states. So the concept of density of states comes in a different context with a variety of symbolic representations. So I think for the time being, we will be introducing the concept of density of states in terms of the number of accessible microstates for a given system. So let me first of all define the density of states as it is given in the slide. The number of accessible microstates which corresponds to the allowed energy states quantum mechanically per unit energy range or per corresponding unit momentum range is what is known as what density of states. And of course, you know, the word density in every sense represents how closely something lies, right? Okay, so density of states, in a sense, we can say that, you know, if there is see a large number of energy states, as you usually describe that, okay, for a quantum system, the energy is discrete, right? Its energy is not continuous. Suppose that I'm taking along y-axis. Usually, you know, for a molecular system, you take along the y-axis the energy of the particles, and if these energy levels are so closely spaced, you think of a case, for example, when you describe the concept of an energy band, you know, in solid state physics, or when you deal with semiconductors and all, we usually consider the concept of an energy band, the valence band and the conduction band. And you know that an energy band is nothing but a range of energy is possible, right? Okay, so when do we define an energy band? An energy band is defined when the energy levels are pretty close to each other, so that we cannot identify exactly one energy level from the other energy level. So there is a continuous distribution of energy levels. Even though the energy is discrete, they are so lying so close that they appear like a continuum. Okay, so in that type of continuous distribution within the discrete nature, we define what is known as density of states. So the density of states in a way represents how closely the accessible energy states or the allowed energy states are lying, okay, for a given system. Okay, so we can say that if the density of states is higher, that there will be large number of accessible energy states for the particle to occupy within a given energy range. And if the density of states is lesser, means what? Within the given energy range, there are lesser number of energy states. So more the density of states, more will be the number of particles that can occupy that given energy range. So the density of states actually plays a very crucial role in deciding the electronic properties or the conduction properties of materials in solid state physics, as well as we can say that the distinction between you can see the whether it's a semiconductor or it's a conductor, everything actually depends on the concept of density of states. So just stick on to the meaning first. Okay, thereafter we can develop the necessary mathematical equations and all. The density of states, okay, the concept should be well and clear. The density of states, as the name suggests, it represents how closely the energy states of a system are lying or arranged. Okay, so it depends. The density of states will be different for different systems. Okay, so there will be a unique density of states for each system. So different systems are characterized by different values of density of states, and which represents how closely the energy states are arranged for that given system. So more the density of states, more number of particles can occupy a given range of energy, say, for that particular system. So that is the meaning, the conceptual understanding of density of states. So now, as let me repeat the definition. You can just refer to the definition. Then the density of states may be defined as the number of accessible microstates. You know, okay, the word microstates we are using in statistical language, and in the quantum mechanical energy picture, we can say that the number of allowed energy states. So from the energy states, the word states in density of states comes. The number of accessible microstates, or from the word microstates, states are here, so the density of states are used here. per unit energy range. So you know that whenever we define something like a density, it will be something like per unit volume or per unit mass, okay, or per unit, okay, whatever it is, okay, for unit of quantity. So here we define it per unit energy range, per unit energy range, or per unit momentum. So there are definitions based on per unit volume also. Here we will stick on to the per unit energy range definition for the density of states in the present context. Okay, so why you can clearly understand that why we have given or per unit momentum, because you know corresponding to a given energy there is a momentum. Okay, corresponding to a given energy there is a momentum. Okay, so for example, for a free particle, you know that for a free particle where only the energy is purely kinetic, you know, okay, the energy E is given by p square by 2m. So corresponding to a given energy there is a given momentum. So you can either talk in terms of the energy of the particles, or you can talk about the momentum of the particle. Okay, so that is the picture that we are going to see. So this equation equal to p square by 2m is to be used for non-relativistic particles having mass, and instead of see that this equation we will have to use E is equal to something like a PC for a relativistic particle like photons or phonons, okay, which are having no mass at all, right? So so here you can see that corresponding to every energy there is a momentum as far as a free particle is concerned, right? So now let's obtain an expression for the density of states, one in terms of the energy and other in terms of equivalent momentum. Okay, that's what we are going to see, and we'll be using this concept of density of states in the later discussions that that's going to follow, especially in quantum statistical mechanics, when we are going to discuss about the energy distribution functions, the Fermi-Dirac function, the Bose-Einstein distribution function and all. We'll be using the concept of density of states later, but I think this is the right time that we introduce the concept of density of states, which you can finally refer back, okay, when it's needed. Right. So let me begin with, you know, to obtain a mathematical expression for density of states, let me begin with the number of total number of accessible microstates. So let me just start with, I'm using the same symbols that is being used in our reference textbook, book for study Petria. So let me represent, let sigma of P. So you remember, I'm just going to define the density of states in terms of the momentum first. Okay, in terms of the momentum first, which we will convert in terms of the corresponding energy, right? So I think the idea is clear to you. Just like, you know, in the case of our descriptions, there are quantities which are corresponding. Here I told you energy and momentum are corresponding to each other, right? Corresponding to every energy there can be a equivalent momentum. Similar to, you know, that in the wave mechanics or in the black body radiation theories and all, you know, either you can draw the graph, black body spectrum as spectral energy density on the y-axis and what the wavelength along the x-axis. You know, instead of wavelength, you can also take the frequency, you know, because corresponding to every wavelength there is a equivalent frequency connected by C is equal to nu, you know, like, you know, just C, nu is equal to C by lambda, or C is equal to C just nu into lambda. So sorry. You can just use what the corresponding wavelength and frequency relationships whenever we need it, because as the properties can be studied either in terms of wavelength or in terms of what the frequency, you know that. So accordingly, whether you are taking wavelength or frequency along the x-axis, the spectral energy density can be either expressed in terms of the frequency u nu d nu, okay, nu, or you can write the spectral energy density in terms of the wavelength. Hope you remember these two expressions. So it depends on whether you are using wavelength of the radiations to represent the system, or you are using what the frequency to use the system. So these two are equivalent, you know that. Okay, these two are what? Equivalent. Much in the same manner, we are using the density of states in terms of momentum, or the density of states can be explained in terms of what the corresponding energy. It's just like, you know, okay, see in a class, you know, okay, in a class of students, okay, so each student is allotted one chair. Okay, suppose that each student is allotted one chair and a corresponding a table, right, or a desk, right? Now the students student can be identified based on either the chair or the corresponding table to which he is belonging to. So likewise, you can identify a system in terms of either its momentum or in terms of its corresponding energy, right? So let me begin with the momentum representation first, and finally I will shift on to the energy representation later, because it's easy to deal with the momentum representation. To begin with the momentum representation, because we are dealing with phase space where one of the coordinate will be momentum, right? That's the reason, only reason why I'm just beginning with the momentum representation. So let me denote, let this sigma of P, let sigma of P, let this be the total number of accessible microstates. Total number of accessible microstates. So always we just specify the word accessible, because you know that all microstates need not be accessible for the particular system. Total number of accessible microstates. Total number of accessible microstates available. I'm considering the simplest of all systems, available to a free particle. A means single, okay? So single particle, a free particle. Okay, I'm taking the simplest of all systems. So we can in general say for a system, okay, for a free particle, which is confined to, a free particle which is confined to move within a volume, confined to a volume, physical volume, what I say, confined to a volume V, physical volume, like a box of dimensions, so that the total volume is V, with momentum between P and just you can take it like 0 to P. I am considering the momentum between 0 to P. Okay, therefore we can say that is by our already existing concepts. Sorry for the disturbances in the background. Okay, so sum of sigma of P, that is the total number of thing, that will be equal to, that's equal to simply by our concept, total number of accessible microstate will be equal to the available phase space volume divided by what is that, the volume minimum phase space volume for the single particle. So that is d raised to 3q integral d raised or d cubed P, okay, divided by what is the minimum phase space volume for a single particle. In 3 dimension it is what, h cube. We have seen that, h cube. So this is nothing but what we have been writing as vq into vp divided by h cubed. Okay, so let me begin from here. Now that for this is for a single particle. Since it is a single particle, that capital N is equal to 1. Okay, otherwise it would have been d raised to 3n q, d raised to 3n p divided by h raised to 3n in the general way. Okay, so this gives you the total number of accessible microstates. Hope you remember I told you earlier that we are using 3 symbols. Okay, we are using symbols like sigma, we are using symbols like gamma, and also we are using what, symbols like what, omega, right? So out of this I'm using the simple sigma. That is why the symbol sigma is used. Hope you remember that I told you sigma denotes usually the number of microstates having energy between 0 to E. 0 to E corresponds to momentum 0 to P, the corresponding momentum 0 to P. That's why we are using the sigma here. Okay, this sigma is corresponding to omega in the other notation that we have been using. So I think it's quite easy to understand this particular concept. So now we are considering the particles to be free, right? For free particles, there is no any interaction. They are acting like point masses. So the volume VQ will be equal to the entire physical volume V of the box, in which, consider that the particle is confined to a box of volume V. Okay, so this is the particle that we are talking about with a momentum P or a kinetic energy E, free particle confined to a box of volume V. So VQ, out of the phase space volume, the coordinate volume will be equal to the physical volume V, because the particle can access the entire physical volume of the space of the box. Okay, so into, what will be Vp? Vp is the volume of the momentum space. Volume of the momentum space. And you know that the volume of the momentum space, usually we calculate it just like what? We calculate like in the momentum space with say that the axis px, we know that, okay, py and pz as the axis, the p as the momentum vector, okay, 0 is the thing. So we consider a sphere in the momentum space having radius is equal to p. So what will be the volume of that sphere? The volume of the sphere should be equal to 4 by 3 pi r cubed. So r is equal to the momentum, pi r cubed, so pi p cubed. So 4 by 3 pi r cubed. So that will be the volume of the momentum space corresponding to the momentum range 0 to p. So v into 4 by 3 pi r cube divided by h cubed. So let me say that this is my equation number 1 to begin with. Alright. So v by h cubed, we can write this one as something like v by h cubed 4 by 3 pi p cubed. Therefore, we need the number of accessible microstates per unit momentum range. Okay. So what is equation number 1 giving? This is the total number of accessible microstates. Okay, within the momentum range 0 to p. So I need it per unit momentum range. So what I have to do? Therefore number of, I have to just make a differentiation, that's all. Okay, number of accessible microstates or energy states, okay, for the system, for the single particle. Okay, here the system is a single particle per unit momentum range. So let me denote that quantity as g, which is a function of p. G is a simple, and I'm writing is a function of p. G of p, that's the way, G of p. So what is G of p equal to? G of p is equal to d by dp of per unit. I have to just differentiate the sigma p, d by dp of sigma of p. Okay, so let me call this equation as equation number 2, and this G of p is by definition given here known as this G of p is known as the density of states. D of p is known as the density of states in terms of momentum. Similarly, we can define G of E in terms of the corresponding energy that we will do at the end. Okay, so G of P is the density of states. Remember, in many authors, they are using either D of E or D of P, okay, for the density of states, capital D. Okay, so D denotes density. So here we are using G, the G of P. That is the thing. So now let us, okay, so that is the number of accessible states per unit momentum range, right? So now I can substitute for sigma of p from equation number 1. So that is equal to d by dp of what is sigma p? That is v by h cubed. I'm writing equation number 1, substituting into 4 by 3 pi p cubed, which is the volume of the momentum space. Which what will be the answer that you will be getting? So it is v by h cubed, 4 by 3 pi will be constant. So for d by dp it will be 3p square, right? So 3 and 3 will be getting cancelled. Finally we are left with v by h cubed. On differentiating we will be getting v by h cubed into 4 pi p square. Okay, so that is an equation that I want you to remember forever. Okay, it's a very, very important equation which we will be using throughout in our later modules. So G of P, okay, G of P, let me write it again in the next page. So the density of states, therefore density of states in terms of momentum represented as G of P, that is equal to, what is that? It is a very easy to remember form. V by h cubed, V is the physical volume available to the system, into 4 pi p square into 4 pi p square. So this equation gives you the density of states. Let me call this one as some equation number 3. So the idea to be kept in mind, the concept to be kept in mind is that density of states is proportional to p square. So this is what I want you to keep in mind, because you may be using these concepts in the next semester while you study solid state physics. Okay, so where you have to always depend upon this particular concept. Density is proportional to p square, right? That's the thing. Now this equation number 3 gives the density of states as a function of the momentum. Okay, now I can use equation number 2. See, what was equation number 2? So equation number 2 gives, equation number 2 was you can see that this is equation number 2. Gp is equal to, definition of density of states, d by dp of sigma p. So what will be therefore a d sigma p? Therefore what will be d sigma p? D sigma p will be equal to gp into dp. You can just cross multiply this one, right? So equation number 2 gives d sigma p, or okay, no, d sigma of p, that will be equal to simply gp dp, right? What is sigma p? Therefore, or I can write it here, therefore, okay, what will be sigma p? What is sigma p that we have begun with? Okay, sigma of p is the total number of accessible microstates or energy states for the system. Sigma p will be equal to, how do you get sigma p from gp dp? So you have to just make a integration over the accessible region of the momentum space. So that is equal to sigma p is equal to integral gp dp, integral gp dp. So this is also a very useful equation for the total number of states. We will be using it. So remember, whenever you have to whenever you know the density of states of a system, okay, either in terms of the energy or in terms of what, the momentum, you can calculate the total number of accessible states for the system by just integrating the density of states with respect to momentum range, or what, with respect to the energy range. So that is sigma p is also equal to integral gp dp, integral gp dp. Okay, therefore the number of microstates, in many cases we are interested to know not the total number of microstates for the system, but the number of microstates that will be having a particular energy range or a momentum range. Okay, rather than a total energy 0 to p, or sorry, total energy 0 to e, or total momentum 0 to p, we will be rather interested in knowing what is the total number of energy states or momentum states lying within a given momentum range p and p plus dp, or say e and e plus de. Okay, I'm going for that one. So therefore number of energy states, or okay, I can use microstates in general now. Of course it can be energy states or momentum states. Number of microstates, okay, number of microstates with momentum, number of microstates with momentum lying between p and some value of p and p plus dp. What's the meaning p and p plus dp? Means within a hypershell, that is in the momentum space, lying within representative points, lying within a hypershell, in momentum space, within the hypershell within the momentum space. Okay, hypershell within the momentum space of thickness, the shell will have thickness dp, right? So that is the meaning. That is given by d sigma p, right? So this is the thing, d sigma p, you know, that is given by d sigma of p. That's the meaning, you know, right? D sigma, like dy or dx. Okay, d sigma p, that will be equal to, what is d sigma p? That is equal to gp dp, right? gp dp, that's equal to gp dp. And what is gp? Which I can substitute as gp is equal to v by equation number 3, v by h cubed for a single particle, v by h cubed 4 pi p square, multiply with the dp. So this is what we can say, that the number of microstates with the momentum ranging between p and p plus dp. Okay, so this is also a useful expression. Remember, these expressions are all closely related, and there is nothing complicated about it. So this we call it as equation number 5. Okay, so this is d sigma p, which is equal to gp dp, right? So that's about it, the density of states in terms of the momentum. Now we are left with a task. In many cases we prefer to express the density of states in terms of the energy rather than the momentum. It's a matter of choice which one is convenient mathematically. We either depend upon the momentum representation, or we will depend upon the corresponding energy representation. Like I told you that we either go for the wavelength representation or the frequency representation. You hope you remember that when we discuss about in the black body radiation, the Wien's displacement law, we better plot wavelength. Okay, and in the Rayleigh-Jeans law, when you do it, we have option either to go for the frequency or to go for what? Okay, the wavelength, okay, so the same manner, it depends. So now we will represent the density of states in terms of the corresponding what you call energy, right? So how to do that? So that's our idea. Now density of states in terms of, that is the same topic only, in terms of, you just have to make a makeover in terms of energy. So remember, we have been using Gp as the density of states. So corresponding to every Gp, there will be a Ge. There will be a Ge. Corresponding to every Gp, there will be a Ge. Where corresponding to momentum, there is an energy. You can see that. So Gp represents the density of states in terms of momentum, and Ge represents the corresponding density of states in terms of the corresponding energy E, right? And see, Ge is usually used for an n particle system, and for a single particle that we are dealing now, usually Petria uses another symbol, that is, instead of G, he is using E, and E is written as a curly letter. So usually A of E is same as G of E in general. G of E is usually for an n particle system that okay, he is using, and A of E is usually what, for a single particle system, where we are discussing the single particle energy states. Okay, so that's what we are, which is the simplest of all systems. In general, remember, it is G of E, right? So we can use either of this one. So we will be deriving an expression for G of E or A of E, whatever it is, doesn't matter. Okay, now so let's see how to start with. So we can start with our already obtained equation for GOP. Okay, we have, or GOP dP. We have GOP dP. What is GOP dP? It is nothing but the number of microstates with the momentum lying between P and P plus dP. Okay, GOP dP is the number of microstates lying between lying with the momentum between P and P plus dP, right? So that is equal to the last equation, V by H cubed into 4 pi P square dP. Okay, so it was our equation that was worth remembering, that I told you. So this is the equation number 5. I'm rewriting it for beginning. So this is our equation number 5 to begin with, right? Now let's rewrite momentum in terms of what? Energy. But that's a quite simple makeover. P is equal to root of 2me, right? Root of 2me. P is equal to root of 2me. Okay, where E is the corresponding energy, right? So for a single particle, let's use this E for that. No worries actually. So that is equal to 2me raised to half, as usual. 2me raised to half, right? So that is P. Therefore, what will be dP? Okay, or I can use the other way also, or I can say that P square, I can do the other way also. P square is equal to 2me. That is the usual equation that we usually begin with. P square equal to 2me. So I have to substitute for P square as well as dP, right? Therefore, I want dP. What do you do? Just differentiate. Okay, so it will be taking differentials on both sides. You can say that therefore 2p dP is equal to 2m dE, right? Taking differential on both sides. So 2p dP will be equal to 2m dE. So 2 and 2 will be getting cancelled out. Okay, or we'll be getting dP equal to I have to just make a corresponding change. dP is equal to, I can write m by p times dE, but p is equal to 2m e raised to half. Okay, so that is equal to m by say root of 2me dE. Now which we can rewrite as, again, this is equal to root of, okay, on combining, root of m by 2e dE, root of m by 2e dE. So dP can be written like this. So p square is equal to 2me, we call it as a, and dP is equal to this quantity, that's b. Now substituting this both a and b in equation number 5. Therefore what will be? Therefore equation number 5 becomes GP dP, that how it is getting changed, that will be equal to V by H cubed, no changes over there, into 4 pi, instead of p square you have to substitute what? P square is equal to 2me, right? Equation A, 2me into dP is what? Root of m divided by 2e. It's quite simple, okay, and straightforward, dE, which we have to, okay, maybe which we have to simplify, and I think we can just simplify it as together, like what is this one? So it's like you can rewrite this one as 2 pi v, just try it out, okay, whether you are getting it as 2 pi v by h cubed, 2 pi v by h cubed, because there is a root 2 here and all, okay, 2 pi v by h cubed. Then what I'm doing, I'm writing it as 2 root 2, what is remaining? 2 root 2 out of 4, say that root 2 is getting cancelled, so it is 2 root 2, and this 2 has been taken here, okay, for some reasons you will understand. 2 root 2, then m raised to 3 by 2, because there is m into m raised to 1 by 2, that is m raised to 3 by 2, then e raised to 1 by 2, is not e raised, because there is e and by root e, so there will be root e remaining, e raised to 1 by 2 d. I think all the factors have been taken care of, okay. So 2 root 2 m raised to 3 by 2 e raised to 1 by 2 dE, right, which can be further written as it's equal to 2 pi v by h cubed, 2 pi v by h cubed into, so can you write this one as 2 into 2 root 2 is what? Nothing but what? I can write is combined, so that is 2m raised to 3 by 2, 2m raised to 3 by 2, okay. So 2m raised to 3 by 2, then e raised to 1 by 2 dE, okay. So you can now see that this is on the right side you don't have any momentum terms, instead you all have the corresponding energy terms. So instead of calling the quantity on the right side as GPdP, it's better to call it as what? The same quantity only, but in a different what do you say, attire, in a different dress, okay, it's dressed up differently in terms of you know, just like energy, okay, see, rather than what, that of the momentum. So we will better call it by another symbol, we will better call it as by another symbol. So what is that symbol? That I told you, like I'll be using AEDE, or remember GEDE for an n particle system later, okay, AEDE, right. So what is your AEDE? So therefore AEDE, the density of states, okay, AE is the density of states, and AEDE is the number of accessible microstates lying between energy range E and E plus dE, right. So that is the meaning of AEDE, right. So AEDE, which is equal to d sigma of E by dE per unit energy range. That's so d sigma E by dE, that's equal to, finally the equation is 2 pi v by h cubed into 2m raised to 3 by 2, 2m raised to 3 by 2 e raised to half dE, e raised to half dE. Let me call this equation also. This gives you the number of microstates, okay, within of a system within energy E and E plus D. That's within a hypershell of thickness dE, right. So that is the thing. Or the density of states in terms of energy. What is density of states? AE is the density of state. Like GE is the density, GP is the density of states. AE or GE is the density of states. So you just get rid of this DE. That's or density of states AE. Okay, is equal to the other thing. Whatever is remaining? 2 pi V by H cubed, 2m raised to 3 by 2, E raised to 1 by 2, DE. Sorry, just get rid of that D, E raised to 1 by 2. So this is what is known as what? The density of states. So remember, for one particle system, single particle density of states, Python is using A of E. In general, it is represented as what? G of E, where E is the total energy. G of E. So that is why I have just given us G of E or A of E. A of E for single particle. Okay, that is n equal to 1, single particle system. That is for single particle density of states, and this is for n particle system. That is a symbol, okay, but in general, okay, we can use G of E because that reduces, right, for n particle system. And so what I want you to remember forever is that G of E is proportional to how is it depending on the energy? You can see that it depends on E raised to half. Okay, G of E. Like I told you earlier that density of states in terms of momentum, how G of E was depending? That was depending on what? P square for every particle. Okay, and you know that P square is equal to what? 2me, or P is equal to what? Root of 2me. So that see where it is P square, the energy dependence will be E raised root of E, P square. Okay, yeah, so you know that when equation bar A you change P, okay, see you can see that it will be root of E will be the dependence. Corresponding to P, it will be root of E. Corresponding to P square, it will be E. That's the reason why the same type of dependence have merged in the final equation here as well. So remember one thing, here we have been considering, as I told you in the beginning, a non-relativistic particle, okay, having mass, right, which is the usual case that we will be dealing with. But remember, statistical mechanics or quantum mechanics has also to deal with relativistic particles without mass. Massless relativistic particle, okay, means which are having the speed of light or comparable to the speed of light. So for example, whenever you deal with what bosons, okay, like say photons or phonons, which are the quantum particles of solid vibration, see phonons, photons, etc. Whenever you substitute for energy, don't substitute E is equal to P square by 2m. Remember, this is for relativistic particles, okay, having mass m. So instead of that, you have to just write E is equal to Pc, okay, or you have to substitute and modify this equation by P is equal to E by C and thereon. Okay, so this equation will not be used for density of states for non-relativistic particles. So that's about the idea of density of states, and will be depending on this concept heavily, both in statistical mechanics, especially in quantum statistical mechanics, fermions and bosons, okay, as well as in the entire solid state physics, and hope that will be of use to you later. See that you preserve this particular topic for your later reference. Okay, read more on it. There are good number of videos available in YouTube by famous teachers. Like there is one thing by Pradeep Haridos of IIT Madras. Okay, I still remember that video. And there are several other videos. Okay, if you want some conceptual clarity, see that you watch those videos again and read it, okay, until you get a picture of concept of your own, okay, on your own concept. That's what we are supposed to do. Because, and beware of one thing, that people will be using large number of different variety symbols for density of states, because it is a very universal concept that appears in many different fields, not only limited to stat mech or quantum mech Okay, because you cannot divide these things into watertight compartments. All these are interdependent. Okay, whatever you study in StatMech will be usually used up in solid state or material science in general, solid state physics. Okay, in every topic that comes, especially when you study about semiconductors, as I told you, you study about the valence band, you study about the conduction band, and the distinction between okay, these materials. You will be using the concept of density states. Okay, so thank you.